All right, let's dive into something that feels like, well, like straight up magic in machine learning. We're going to tackle how one of the most powerful algorithms out there, XGBoost, can learn from data that is completely, totally missing.
And look, this is a real head-scratcher. You're always told that machine learning models need clean, complete data to work. So how on earth can one of the best models in the world make incredibly smart decisions based on, well, nothing? A total black hole of information?
And hey, if you're confused by this, you are not alone. This is a real post from a user on Data Science Stack Exchange, and it just nails the confusion perfectly. It feels like there has to be a trick, right? Some secret value it's plugging in behind the scenes. But the real answer is so much cooler than that.
So, to really appreciate why XGBoost's solution is so brilliant, we first have to talk about why missing data is usually such a total nightmare for pretty much every other algorithm out there.
Yep, that's the deal. For most models, if you try to feed them data with blank spots, they'll just error out, stop working. The workaround is something called imputation, which is really just a fancy way of saying you guess the missing values. Fill them in with the average or the median. The problem is, it's still a guess, and a bad guess can seriously mess up your whole model.
So how does XGBoost get around this whole guessing game? Simple. It doesn't guess. Not at all. Instead, it has this really elegant, built-in strategy for dealing with these gaps in the data.
Okay, so the fancy official name from the original paper is Sparsity-aware split finding. I know, it sounds a bit intimidating, but the core idea is actually super clever. Instead of you having to fix the missing data before you train the model learns the best way to handle it during the training process itself. It basically makes the missingness part of the pattern it's trying to learn.
And this visual right here explains it perfectly. So think of a decision tree as just a series of yes or no questions. At each question, there's a fork in the road. You go left or you go right. What XGBoost does is add a third path, a default direction. So if a piece of data shows up and say the age is missing, it doesn't get stuck. The model has already figured out which way, left or right, is the best path for any missing values at that specific fork in the road.
Okay, so that leads to the crucial question. How does it learn that default direction? This isn't some pre-programmed rule. It's a decision the model makes by looking at the data. This is where the real magic happens.
Here's the play-by-play. At any decision point, the data gets split up. Let's say the known values go into Group B or Group C. Now all the data points with a missing value get put into their own little squad. Let's call it Group M. The algorithm then runs two little experiments. First, it pretends to send Group M to the left with Group B and calculates what's called a gain score, which is just a measure of how good that split is for the model. Then it tries sending Group M to the right with Group C and calculates a new score. Whichever direction gives it the bigger score, the bigger improvement, that becomes the permanent default direction for that node.
But wait a second, this brings us right back to the original mystery, doesn't it? How in the world can you calculate a score based on a value you don't even have? If you don't know the feature, how can you possibly know if the split is any good? It feels like we're running in circles.
And here it is. This is the big reveal, the secret sauce. It has absolutely nothing to do with the missing feature itself. It has everything to do with the one piece of information that we do have for every single one of those rows.
That's the key. XGBoost looks at the outcome, the answer, the target label you're trying to predict. Think about it. Even if a customer's age is totally missing from your data, you still know whether they bought the product or not, right? The algorithm uses that known outcome, that final answer, to figure out which path is the best one. So when it runs those two tests we talked about, the score is all about how well each option separates those final outcomes. It's asking, for instance, does sending the missing age customers to the left, maybe with the under 30 crowd, do a better job of separating the buyers from the non-buyers, or does sending them to the right work better? The algorithm just picks whichever path sorts the final results most cleanly and reduces the most error. It's brilliant.
Now, this isn't just some neat little academic trick. This whole sparsity-aware approach is one of the main reasons XGBoost is an absolute legend when it comes to real-world performance. Let's take a look at just how powerful this is.
Get this, back in 2015, on the machine learning competition site Kaggle, out of 29 winning solutions, a staggering 17 of them used XGBoost. That's just insane dominance. Its ability to just chew through messy, real-world data with tons of missing values without needing a bunch of careful pre-processing made it an absolute monster.
And it's not just that it's smart, it's that it's wickedly fast.
This chart, based on data from the original XGBoost paper, is just mind-blowing. On this one particular dataset, the sparsity-aware algorithm was over 50 times faster than a more basic version. 50! By cleverly ignoring the missing values and only focusing on the data that's actually there, it gets a massive speed boost.
So let's just recap why this is such a game changer. First, you save a ton of time on data cleaning because you just don't need to do imputation. Second, the algorithm is lightning fast because it's built for this exact scenario. And third, and this is maybe the coolest part, it can actually learn that the very fact a value is missing is predictive. Maybe people who don't list their age all belong to a specific group. The missingness becomes its own feature.
And that really leaves us with a final, fascinating thought. What XGBoost teaches us is that an absence of information can, itself, be incredibly informative. So it makes you wonder, what other patterns, hidden in the gaps and the empty spaces of our own datasets, are we just completely failing to see?